The last major topic that we are going to talk about in this class, because we only have, let's see, today and then all next week as new content days, basically. The last day of class will focus on working on the project, because that's when it'll be due, and overall review for the class. So basically we have today plus 3 additional days of new content. And what we're going to be talking about is transient systems. So in our overall balance equation, we have in minus out plus generation minus consumption is equal to accumulation. And for 99% of what we've been working on, we will say that this is equal to 0, which is the case for a steady state process. For a material balance, we can get rid of generation, we can get a consumption. For an energy balance, we can get rid of generation, we can get rid of consumption. For mole balances, we have to keep these 2 terms. So most of our attention has been focused on just these 2 aspects of the process. In for mass balances is pretty straightforward. Mass in, mass out. In and out for energy, there were a couple different ways that we had energy coming in and out of the system. Right? We had work energy coming in and out. We had heat energy coming in and out. But what we're going to be doing now is now focusing on including this accumulation term. Now, the only way that this can be interesting then is if the in-out generation and consumptions are changing as a function of either time or changing as a function of a result of the process conditions. So essentially, the entire junior year of the chemical engineering curriculum is focused on this aspect. Right? If it's dm dt or dc dt, right, that corresponds to a mass transfer class. Right? How quickly can we get mass in and out of the system? The system is going to be a bit different as well. It's not going to be a unit operation, it's going to be a differential element. So we're going to take the concepts that we learned in this class and not apply it to a unit operation, which has a wall and a boundary and pipes coming in and pipes coming out, but rather a mysterious element called a differential element, which is going to have some box size, dx, dy, and dz. We're not going to focus too much on the differential material balance, but this is really the future of your class curriculum, is transitioning from big unit, big chemical plant, to a small unit differential. So what's happening in this balance is that I have material flowing in and out from all different directions. And I'm going to keep track of how much mass or energy is stored within this differential element. Now, if we apply this concept, the accumulation term in the case of mass and energy balances, let's say is dm, actually let's say dE dt for an energy balance, okay, because that's what we're talking about. So the total energy, better write that as U, the total energy coming in and out of this particular process here is going to be proportional to the material properties. This is going to be proportional to the temperature difference. And this is essentially then what you'll be accomplishing in the heat transfer class, is to reapply everything that we've done in this class, but shrink it down to a box of dx, dy, dz. Now what happens when we do this is that what we're dealing with is only changes as a function of time. But when we add in x, y, and z parameters, this ordinary differential equation is going to turn into a partial differential equation. So mass balance is the same concept here, except as opposed to U, it's M. We're going to be turning the ordinary differential equation into a partial differential equation. So mass and energy balances, you're actually solving exactly the same equation. So a lot of universities don't have 2 separate classes, they just have one transport phenomena class. Your reactor design, you're going to be doing exactly the same thing. It's going to be mass balance, but you're going to be spending a lot of time on the generation and consumption terms. What is the local concentration inside of this volume element of fluid? how fast does the reaction occur to generate or consume different species. And from there, you're going to have reaction rate laws. Right? The faster the rate, the more quickly this converts from this cell to this cell to this cell to this cell. And when you add those all together, that's how you get the partial differential equation. For us, we're going to do a little bit of this just to kind of introduce you guys to what's going to happen in junior year, but for the most part, we're going to be playing around with just ordinary differential equations. I'm not going to expect anyone to solve any PDEs, but you are definitely expected to solve ODEs for the last little bit of the class. So this is kind of a general setup to what we want to do. So this is, in essence, an introduction to the entire junior year. So here, we're doing big picture, junior year, local picture, microscopic level, differential elements of fluid. Senior year, you're back to the big picture again, putting all the pieces of the puzzle together, right, from the sophomore through the junior, and then trying to build the chemical plant. Okay, so let's go through a couple of examples of how we would rewrite our equations for different material balances. So for transient material balance, transient mass balance, now the approximation we can use in a material balance, mass balance, because of systems, what terms go away in my general balance equation for mass balances? You can have any generation or consumption of mass. We are not dealing with nuclear processes. So, dm dt, now this is the mass contained within the entire process. In the case here, that's a differential element. In the case here, this could be the entire mass contained within a bucket of water, or a bathtub, or a reactor, or a heat exchanger. And this is simply just going to be summation of mass in minus the summation of mass out. But in order to make this interesting, the mass flow rate in should be changing either as a function of time or as a function of maybe the total mass of the system, or maybe it'll change as a function of the mass out if you have some sort of a controlling process. But what makes this interesting is when these things are now functions of either time or parameters in the system. And that way we can introduce some physical laws and some reality to the process. So for example, if we have time, we'll go into this particular scenario. If I am draining a tank of water, or a bathtub, or a sink, the water level has some height h. The flow rate out of the system is going to be proportional to the height of the system. In addition, some other, parameters about the piping, the pressure loss, and all that. So this would be a problem you would solve in a fluid mechanics type class. Because hydrostatic pressure, the pressure gets higher the lower you go. The higher the pressure here, the more it's going to want to push out of the piping system itself. And this is something we all have good physical evidence of, right? If you pull a plug on a tank, it drains really quickly, and then it slows and slows and slows and slows. That's because the pressure drop across this section has gotten smaller and smaller and smaller, so the flow rate reduces. So that would be an example of a differential mass balance. Next, let's talk about mole balances. Now, in the mole balance, we cannot assume that the generation and consumption are equal to 0, because that's really what we care about when we commit to ourselves to doing a mole balance. So we'll have dn dt. Now, this could be the total number of moles, or this could be the number of moles of species I, right? We have the same rules and opportunities with steady state balances as we do with transient balances. You can do one per every species in the system, and you can also do the total species balance. Right? But again, degrees of freedom still hold true. One of those is going to be dependent on the others. Material flowing in, material flowing out. No big complications there, exactly the same as the mass balance. But in the mole balance, we have generation and consumption terms. Now, these are going to be very important when we have reactions. So, for example, the rate of consumption is going to have units of moles versus moles over time. Right? How quickly are we consuming or generating material? But what makes this interesting and relevant to expand on in an entire class, your reactor design class, is this is going to be equal to V times by some reaction constant and some rate law. Volume of the reactor, going to have units of volume. Your K is going to depend based on your reaction rate, and your concentrations are going to be moles per volume raised to some power. So the reaction rate constant units are sort of picked to make it all work out nicely. But different chemical reactions obviously occur at different rates. They have different reagents. Those reagents have different power laws, right? Some are first order, some are second order, some have some nth arbitrary order. If it's a catalytic process, you'll maybe rewrite this as an approximate form based on how good your catalyst is, for example. But the key part to a transient mole balance is then to introduce specific rate laws that are representative of the physical process to actually model this reactor in real time. Now, in the case of your reactor design class, you'll be playing around with these differential elements and playing around with mole balances for the entire reaction to figure out if I change the geometry or the flow pattern or how I introduce the reagents, how does that affect the overall rate, the required volume of the reactor, and the conversion that I can get out of a reactor of a particular volume. Right? So PFR versus CSTR. Next, we have transient energy balances. Now, I want to spend a bit of time talking about the energy balance because we haven't gotten back to the original form of it since we started the reacting systems. We've been focusing on the heat of reaction method or the heat of formation method. But just as with the transient mass and the transient mole balance, we're still following the general balance equation, right? Accumulation is equal to in minus out plus gen minus consumption. Now, in the case of an energy balance, we cannot have any generation and consumption. So it's just in minus out. So if at any point you forget the energy balance equation, just remember in minus out. So du dt, the total internal energy of the system, right, which is our stand-in for the total energy basically, per unit time, this is our accumulation term. All we're doing is adding up all the sources of energy in and subtracting all the sources of energy out. So we have energy entering in the form of enthalpy with the molar or mass flow rate coming into the system. Right? Sometimes this could be m dot, sometimes it's n dot. It just depends on what your units of specific enthalpy are. Right? So if you're doing a steam tables problem, you'd want to write this as m times h as opposed to n times h. Because it's just the units you have to go. We have energy leaving the system in the form of mass, right? The energy stored in the bonds, the vibrations, translations, all that. And with heat, we can have heat passing through barriers, whereas mass can't. So we can have heat energy in, and we can be extracting work out. Now, the conventions here are not strict, but just remember, do the plus and minus arrows based on how you draw your process. So if you have a heat exchanger, energy has to be minus at one and plus at the other, otherwise it's going to mess things up a lot. So a lot of people will fret and worry over positive work and negative work, and there's textbook wars over which is the best way to do it, but ultimately I don't think it matters. Just draw it. If you draw an arrow into your system, you plus it into your balance. If you draw an arrow out of your system, you minus it in your balance. The only reason why it really matters is in theoretical derivations. And actually, it's easier to have work be negative because then it makes the enthalpy derivation much cleaner as being plus PV, because when you move this over there and all that kind of stuff. So now how do we introduce sort of new interesting physical laws into this particular process? So what we'll do is we will typically rewrite this in a slightly different form to make it something that we care a little bit more about. U is important, but it's really not something that's particularly easy to follow along with. So what we'll do, actually let me do one step before this one. So what makes this process interesting is that the rate of heat transfer is proportional to the temperature difference. Right? So if I put a really hot and a really cold two things together, the temperature change of each of those will be very rapid. If I put two kind of cool and kind of warm things, it'll take a long time for them to change. Right? So the bigger the temperature difference, the quicker the temperature will change. And how we mathematically represent this is the rate of heat transfer is going to correspond to the area available for heat transfer times by a heat transfer coefficient. This describes the conditions, what is the pipe made of, how quickly are the fluids flowing, what are the materials of the fluids, and then times by some temperature difference. So A is going to, for example, have units of area. Heat transfer coefficient is going to be joules per meter squared per second per Kelvin. Or you could also write this as watts per meter squared Kelvin as a rate of heat transfer. And then your delta T is just going to have units of temperature or Kelvin. So when you work this all out, we get watts for the heat transfer coefficient. Now the problem is, if I substitute this expression into here, I have an issue. I have a dependent variable, u, and no u's anywhere else. So what we'll want to do is rewrite the u in terms of temperature so that we can actually solve this ordinary differential equation. So what is typically done then is that we will write du dt a slightly different way. We'll write it as mc sub p dt dt. And so if we look at the units, the mass would be kilograms, c sub p would be joules per kilogram Kelvin, and this is going to be Kelvin per second. And it gives us the right units of joules per second. What approximations or assumptions have I made in doing this process here? Constant C sub P is the main one. But for the most part, this is the way that we'd be solving problems in a heat transfer class. So basically, transient material balances, we have fluid mechanics, reactor design, heat transfer, and then when it comes to the actual design of separators like adsorbers, distillation columns, liquid-liquid extractors, you have your separations class. Furthermore, we have also talked quite a lot about how when it comes to enthalpy changes or property changes of real fluids or predictions of thermodynamics for complex non-ideal mixtures, that's why we need Thermo 2. So basically, from transient balances and filling in all the properties, every single one of your major junior classes is covered in here. There's also some other ones, like a bioengineering that corresponds to how do you design fermenters and bioprocesses. But for the most part, what we're talking about now and where we're wrapping up transitions us perfectly into the next year of the chemical engineering curriculum. So, let's do one quick example of how we can apply transient systems, and it builds on here draining a tank. So the setup here is going to be the same as that little drawing that I did over there. We have a tank. It has some initial h with an h naught, an initial height. And we have some volumetric flow rate out of the system, or rather, I'll just say mass flow rate out of the system that we don't know quite yet. So the initial mass, so I'll call it m naught, is going to be equal to, let me draw it on this out here, the tank diameter. We have a tank diameter, we have a height, we'll say it's a cylindrical tank. Pi d over 2 squared times rho h naught. Let me write h naught rho. This is the volume of the fluid initially. This is the density. The rate of mass out of the system, we're going to say, is proportional to some constant times by the height in the system itself. Now this is just a direct application of the concept of hydrostatic head. The higher the water level, the higher the pressure at the bottom of the tank. And what's driving this real process is the pressure drop through the piping. This is at atmospheric conditions, let's say in this example. Here is at non-atmospheric conditions. Flow is driven by pressure differences. So the higher the pressure difference, the more the fluid wants to get out. But if I add a valve into the process here, I can increase the pressure drop, meaning I need a greater pressure difference between the inside and outside to have the same flow rate. So based on how I build my piping here and how much pressure loss is associated with it, that controls how quickly my tank will drain. And what the valve is doing, the valve is varying how much pressure loss there's going to be. This is always going to be atmospheric. This is always going to be the pressure associated with hydrostatic head. And that's how we determine how quickly things will drain. So now I believe we have all of the information we need to actually solve this particular problem. If this was a real fluid mechanics class, you would be solving for what this K constant would be. Right? You might call it something different, but essentially you're looking for a proportionality constant between the height of the fluid and this. But it would, in your fluid class, would be more related to, the pressure drop across here. So let's do our calculus or differential equations, however you want to think about it. So dm dt is going to be equal to m dot in minus m dot out. This is 0, which is going to be minus kh. We have a problem. This is in units of m. This is in units of h. So we need to do a little bit of algebraic or calculus manipulation. So we're going to take this formula here for our initial mass, and we're basically going to differentiate it. So m is equal to pi d over 2 squared h times rho. So I'm going to take the derivative with respect to time to both sides of the equation, and I get dm dt is equal to pi d over 2 squared times rho dh dt. Substitute it into my material balance. And I'll do a little bit of rearranging. dH, it's a total differential, not the partial. dH dt is equal to minus k over pi d over 2 squared times by rho. I'm going to call that A to make it simple on my math, and times by H. So to rewrite that, this will be minus AH. To all the calculus and Diffie-Q whiz kids in the class, what is that derivative? What is the integral of that solution?
Exponential.
It's an exponential. it is straightforward enough that we can solve it by separation of variables. So we move the dt to one side, the h to the other side. We have dh over h is equal to minus a dt, which means we can integrate each of these independently. Okay, so integrating 1 over x or 1 over h is what? Natural log. Integrating a constant minus a t plus a constant of integration.
Isn't that natural log of h?
Oh yeah, sorry. That's right. Solving for h, take the exponent for both sides. H is equal to c prime exp of minus a t.
What'd you call c prime?
Because it's not c, it's actually the exp of c.
Oh,
Just from exponent laws.
okay.
Because if you take the exponent of things added together, you can break them apart and multiply them.
Right.
Just to be clear, this is equal to exp of minus a t plus c, which is equal to exp of minus a t times by exp of c, and I call this c prime. Next part, solve for the initial conditions. We need to know what our constant of integration is. So at t equals 0, h is equal to h naught. So at t equals 0, this goes to 1. So h is equal to h naught exp of minus a t. This started off as a mass balance. Everything you will do in chemical engineering is either a mass balance, mole balance, energy balance, or thermodynamics. Except for controls. Controls is sort of a different monster. Every single thing that you will do in your entire chemical engineering curriculum should start as either mass, mole, energy, or thermodynamic calculation. So this class basically covers all of the fundamentals of the entire chemical engineering curriculum. Now, that may not look like it going forward in the future, right? As soon as you derive these partial differential equations based on these differential elements, you might forget that they started off as mass balances or mole balances. But everything is either a mass balance or an energy balance, basically. So if we were to plot this out just quickly before everyone runs off, it is just a decay. So the h as a function of time. So as the tank gets lower, the rate of change, right, dh dt, gets smaller as time progresses and the tank level gets lower and lower and lower. So what we're going to be doing for the next couple weeks in the class is we're going to be basically deriving a lot of the expressions that you may see going forward and showing how the content and the transient level really applies to sort of the fundamentals of chemical engineering throughout. All right, please get the project in. Don't be late. There will be a penalty. Midnight is the deadline. And unfortunately, I will not necessarily be available at all today. So good luck, everyone. Take care.